A very good morning to all of you. I am Dr. Naveen Kumar Devangan, Professor in the Department of Electronics and Telecommunication Engineering, Bhilai Institute of Technology, Durg. It is a great pleasure to be here today with you all and talk about the exciting world of biomedical instrumentation and sensors in the fascinating realm of ultrasound imaging. First of all, we will start with introduction of ultrasound imaging. There we will see ultrasound imaging as a non-invasive and painless procedure to provide precise images of the body's internal organs and tissues. We will also see why ultrasound imaging is preferable as a diagnostic tool over X-rays or MRI imaging in certain cases. Then we will see physics of ultrasound. There we will see frequency and characteristics of ultrasound. Then we will see principles of ultrasound imaging. There we will see when an ultrasound beam is made to fall on interface of two different medium, it obeys laws of reflection and refraction. It is reflected beam which is converted into image form for taking diagnostic decision. Then we will see how ultrasound interact with different body tissues. Then I will talk about production of ultrasound, and there we will also see why these three parameters, frequency, active element diameter and focusing, are important in ultrasound imaging. We will also talk about image construction and various imaging modes, and we will also see a typical ultrasound machine and general block diagram of ultrasound machine. We will see procedure of ultrasound and in very brief advantages and applications of ultrasound imaging. Now we are going to see brief introduction of ultrasound imaging. Ultrasound has become increasingly important in medicine and has taken its place along with X-rays and nuclear medicine as a diagnostic tool. Its main attraction as an imaging modality lies in its non-invasive character and ability to distinguish interfaces between soft tissues. In contrast, X-rays only respond to atomic weight differences and often require the injection of a denser contrast medium for visualization of non-bony tissues. Similarly, nuclear medicine techniques measure the selective uptake of radioactive isotopes in specific organs to produce information concerning organ function. Radioactive isotopes and X-rays are thus clearly invasive. Ultrasound is not only non-invasive, externally applied and non-traumatic, but also apparently safe at the acoustical intensities and the duty cycles presently used in diagnostic equipment. Diagnostic ultrasound is applied for obtaining images of almost the entire range of internal organs in the abdomen. These include the kidney, liver, spleen, pancreas, bladder, major blood vessels, and of course the fetus during pregnancy. It has also been usefully employed to present pictures of the thyroid gland, the eyes, the breasts, and a variety of other superficial structures. In a number of medically meaningful cases, ultrasonic diagnostics has made possible the detection of cysts, tumors, or cancer in these organs. This is possible in structures where other diagnostic methods by themselves were found to be either inapplicable, insufficient, or unacceptably hazardous. The main limitation of ultrasound, however, is that it is almost completely reflected at boundaries with gas and is a serious restriction in investigation and thorough gas containing structures. Now we are going to see physics of ultrasonic waves. Ultrasonic waves are sound waves having frequencies above the audible range, that is greater than 20 kHz. These waves exhibit the same physical property as the audible sound waves, but they are particularly preferred in situations favored by one or two of the following reasons. First, ultrasonic waves can easily be focused, that is, they are directional and beams can be obtained with very little spreading. Second, by using high frequency ultrasonic waves which are associated with shorter wavelengths, it is possible to investigate the properties of very small structures. It is particularly true in the detection of defects where the wavelengths utilized should be of the same order as the dimensions of the defect. Transmission of ultrasonic wave motion can take place in different modes: longitudinal, transverse or shear. However, for medical ultrasonic diagnostic applications, the longitudinal mode of wave propagation is normally used, as these waves can be propagated in all types of medium, for example solids, liquids and gases. In longitudinal waves, the particles of the medium oscillate to and fro in the direction of the propagation of the wave, resulting in alternate regions of compressions and rarefactions. Now next, I am going to explain principles of ultrasonic imaging. Ultrasonic frequencies employed for medical applications range from 1 to 15 megahertz. The velocity of ultrasound in a medium is dependent on density of the medium, its elastic properties and the temperature. It is also frequency dependent. In normal applications, ultrasound is actually focused into a beam which obeys laws of reflection and refraction as shown in figure 1. It is the reflected beam which is of paramount importance in image formation in ultrasonic imaging. Now I am going to explain how ultrasound interact with tissues of the body. The characteristic impedance of the mediums determines the degree of reflection and refraction at the interface between two media. The reflected energy is dependent on the difference of densities between the two media and the angle at which the incident beam hits the medium. The percent of the incident wave energy which is reflected is given by Z1 minus Z2 upon Z1 plus Z2 whole square into 100, provided the ultrasonic beam strikes the interface at a right angle, where Z1 is the acoustic impedance of medium 1 and Z2 is the acoustic impedance of medium 2. Characteristic impedance or specific acoustic impedance of a medium is defined as the product of the density of the medium with the velocity of sound in the same medium. So, Z is equal to rho V, where Z is the specific acoustic impedance of the medium, rho is the density of the medium and V is the velocity of sound in that medium. The greater the difference in acoustic impedance, for example tissue and bone or tissue and gas, the greater the amount of reflected energy and almost no energy will continue through the second medium. For example, the acoustic impedance of air and tissue are 42.8 gram per centimeter square second and 1.6 into 10 to the power 5 gram per centimeter square second respectively. This difference is so large that most of the ultrasonic energy tends to be reflected at the interface. In other words, ultrasound propagation path must not include bone or any gaseous medium or air. For applying ultrasound to the skin, an aqueous gel or water bag is placed between the transducer and the skin to provide an airless contact. The approximate value of acoustic impedance for most of the biological materials or organs is the same. It is about 1.6 into 10 to the power 5 gram per centimeter square second. When an ultrasonic beam travels through a medium, its amplitude can decrease due to the medium's absorption as well as its deviance from the parallel beam by reflection, refraction, scattering and diffraction, etc. The relative intensity is expressed in decibel and the attenuation of an ultrasound beam is expressed in decibel per centimeter. Table 1 shows velocity of ultrasound, characteristic impedance and absorption coefficient in various materials. We can see that the velocity of most body fluids is around 1515 meter per second, that is higher than water. The velocity through bone is 4080 meter per second, whereas through fat is much lower, 1450 meter per second. Absorption of ultrasound is least in water and blood and highest in case of bone. Now I will talk about the resolution of an ultrasound system. The resolution of an ultrasound system can be defined as the system's ability to distinguish between closely related structures. Axial resolution is the minimal axial distance parallel to the beam axis at which two reflecting structures are recognized as separate structures. This you can see in figure 2a. The axial resolution is determined by the wavelength of the transmitted pulse. This means that the smaller the wavelength, the higher the frequency and better the axial resolution. Lateral resolution is the lateral distance in a plane perpendicular to the beam axis at which two reflecting structures can be seen as two separate structures. You can see in figure 2b. The lateral resolution is determined by the shape or divergence of the ultrasound beam produced by the probe or transducer. You can see in figure 2 how axial and lateral resolution is illustrated. Now I will talk about generation and detection of ultrasound. The physical mechanism normally used to generate and detect ultrasonic waves is the piezoelectric effect exhibited by certain crystalline materials. These materials have the property to develop electrical potentials on definite crystal surfaces when subjected to mechanical strain. The converse is also true, which means that mechanical displacement is produced when electrical charges are put on their surface. The crystals of materials like quartz, tourmaline and rochelle salt shows piezoelectric effect. While working with natural crystals, it is difficult to stabilize the appropriate axis and cut the crystal in the required form. Therefore, quartz has generally been replaced by synthetic piezoelectric materials, namely barium nitrate and lead zirconate titanate. They offer several advantages because they are far cheaper to produce and are much easier to construct transducers of complex shape and large areas. They can be molded to any shape to obtain a better focusing action for producing high intensity ultrasonic waves. The choice of piezoelectric material for a particular transducer depends upon its applications. Materials with high mechanical Q factor are suitable as transmitters, whereas those with low mechanical Q and high sensitivity are preferred as receivers, and in case of non-resonance applications. Lead zirconate titanate, in short, PZT crystals are much better than quartz crystals up to a frequency of about 15 MHz because of its electromechanical conversion efficiency and low intrinsic losses. PZT can operate at temperatures up to 100 degrees centigrade or higher, and it is stable over long periods of time. It is mechanically strong and can be machined to various shapes and sizes. At frequencies higher than this, quartz is normally used because of its better mechanical properties. Polyvinylidene difluoride (PVDF) is another ferroelectric polymer that has been used effectively in high frequency transducers. The surface of the synthetic crystals is normally silvered for making external electrical connections. Piezoelectric crystals are available in several shapes, and the selection of a particular shape depends upon the application to which it is to be put. The application of a voltage to the transducer disc causes changes in its thickness, thereby giving rise to longitudinal waves propagated along the axis perpendicular to its face. The magnitude of the waves will be a maximum at the resonant frequency of the disc, which is determined by its thickness. Likewise, when the transducer is acting as a receiver, it will be most sensitive to ultrasonic vibrations at its own resonant frequency. Therefore, considerable attention is devoted to tailoring the dimensions of the transducer to the frequency at which it will be used. There are three parameters that are important in optimizing transducers for various types of applications. These are frequency, active element diameter, and focusing. Their effects on the performance are as follows. We are going to see effect of frequency on the performance of ultrasound imaging. With increase in frequency, the sound beam becomes more directional and the axial resolution improves. However, due to attenuation of higher frequency ultrasound waves in the tissues, the penetration decreases. For most abdominal ultrasound examinations, the frequencies used are in the range of 1 to 5 MHz, whereas the wavelength is in the range of 1 millimeter. Higher frequencies from 10 to 15 MHz are used for superficial organs such as the eye, where deep penetration is not required and where advantage may be taken of the 0.1 millimeter wavelength to improve geometrical resolution. We are going to see effect of active element diameter on the performance of ultrasound imaging. As the transducer phase diameter increases, the beam width decreases and therefore lateral resolution improves. The choice of which element size to use is generally based on two considerations. First, where on the patient's body the transducer is to be positioned, and second, the depth in the body to the structures of interest. While it is often desirable to use a large diameter to reduce beam divergence, this is sometimes not practical. For example, many times in echocardiography, a patient will have very narrow intercostal spaces necessitating the use of small diameters. In thyroid applications, the area to be scanned is irregularly shaped. Consequently, small diameters are helpful in maintaining good contact between the patient and the transducer. General abdominal and pelvic examinations usually do not have restrictions such as this, and large diameters can be used easily there. The second point to consider is the depth in the body you wish to image. For the best image detail, it is advantageous to have the ultrasonic beam as narrow as possible to achieve minimum divergence. For superficial structures, the beam must narrow very close to the transducer face, and lateral resolution at greater tissue depth is not critical. Therefore, small diameter transducers are indicated. When the structure of interest lie deeper in the body, for example pelvic and obstetrical examinations, obese patients, large diameters are advised, since their decreased rate of beam divergence becomes important at greater tissue depths. Now we are going to see effect of focus on the performance of ultrasound imaging. Focusing a transducer is a mean of minimizing the beam width and adjusting the focal zone to give optimum results for a particular examination. Acoustic lenses can be used to shape the ultrasonic beam pattern. The width of the beam can be made narrow, with the result of the better lateral resolution can be obtained. The focal point can be selected at different depths from the face of the transducer. The ability to select different focal points allows for the optimization of transducers for a particular type of studies. Modern transducers are internally focused and externally are of flat face. While selecting a transducer for a particular application, all three of these factors, frequency, active element diameter and focusing, should be carefully weighed to achieve optimum performance. Now we will see how is an ultrasound image formed in the monitor. The amplitude of each reflected wave is represented by a dot. The position of the dot represents the depth from which the echo is received. The brightness of the dot represents the strength of the returning echo. These dots are combined to form a complete image. Strong reflections are represented by white dots, for examples from pericardium, calcified structures, diaphragms, etc. Weaker reflections are represented by grey dots, for example from myocardium, wall tissues, vessel walls and liver, etc. No reflections are represented by black dots, for example intracardiac cavities, gallbladder, etc. Various imaging modes found in today's ultrasound system are: first, A mode we call amplitude imaging. It displays the amplitude of a sampled voltage signal for a single sound wave as a function of time. This mode is considered one-dimensional and used to measure the distance between two objects by dividing the speed of sound by half of the measured time between the peaks in the A mode plot, which represents the two objects in question. Second, M mode motion display. It refers to scanning a single line in the object and then displaying the resulting amplitudes successively. This shows the movement of a structure such as heart. Because of its high pulse frequency up to 1000 pulse per second, this is useful in assessing rates and motion and used extensively in cardiac and fetal cardiac imaging. Third, B mode, we call it brightness imaging, is the same as A mode except that brightness is used to represent the amplitude of the sampled signal. B mode imaging is performed by sweeping the transmitted sound wave over the plane to produce a two-dimensional image. Typically, multiple sets of pulses are generated to produce sound waves for each scan line. Each set of pulses are intended for a unique focal point along the scan line. Continuous wave Doppler. Fourth one, here a sound wave at a single frequency is continuously transmitted from one piezoelectric element and a second piezoelectric element is used to continuously record the reflected sound wave. By continuously recording the received signal, there is no aliasing in the received signal. Using this signal, the blood flow in veins can be estimated using the Doppler frequency. However, since the sensor is continuously receiving data from various depths, the velocity location cannot be determined. Fifth mode, pulse wave Doppler. In this mode, several pulses are transmitted along each scan line and the Doppler frequency is estimated from the relative time between the received signals. Since pulses are used for the signaling, the velocity location can also be determined. Sixth mode, color Doppler. The pulsed wave Doppler is used to create a color image that is superimposed of the flow. Red typically denotes flow towards the transducer and blue denotes flow away from it. A darker color usually denotes a larger magnitude while a lighter color denotes a smaller magnitude. Now coming to medical ultrasound is the imaging of internal organs or structure of the body is on the basis of ultrasound principles. This gives information regarding size, location, displacement or velocity of a given organ without surgery or any harmful radiation. Tumors can be easily identified. Ultrasonic techniques avoid risky or painful procedures. Imaging systems are comprised of the pulsed ultrasound or pulsed Doppler mode. Applications making use of continuous waves depend for their action on Doppler's effect. Among the important commercially available instruments based on this effect are the fetal heart detector and blood flow measuring instruments. There are, however, many applications where only pulse waves can be employed. In fact, the majority of modern ultrasonic diagnostic instrumentation is based on the pulse technique. Pulse echo based equipment is used for the detection and location of defects or abnormalities in the structures at various depths in the body. This is possible because the time of travel of a short pulse can be measured with much greater ease and compared to continuous waves. Echoencephalograph, echocardiograph and ultrasonic scanners for imaging are all based for their working on the pulse technique. Now we are going to see modern ultrasound imaging systems. They make use of digital signal processors and systems on chips which are specially designed single chip microcomputers that process digitized electrical signals generated by the transducers. A diagnostic ultrasound imaging system generates and transmits acoustic waves and captures reflections that are then transformed into visual images. The signal processing on the received acoustic waves include interpolation, decimation, data filtering, and reconstruction. The basic functional building blocks of a diagnostic ultrasound imaging system are the transducer, processing blocks needed for image formation, system controller, and power supply module as shown in figure 3. Delineation of signal path operations as front end, mid end, and back end processing varies from one manufacturer to another. Figure 3 shows ultrasound imaging system functional blocks. The transmit beamformer is responsible for the pulse excitation of transducer elements, which results in emission of acoustic waves into the region of interest. Immediately following this, the transmit receive switch, we call it as TR switch, is positioned to put the front end in receive mode. Transducer elements transform the reflections or echoes into corresponding electrical signals. The analog front end AFE properly amplifies these signals and converts them into digital data streams for further processing. By applying dynamic delays into these data streams, the receive beamformer combines them to form a scan line, a representation of the region of interest along a given line of sight. This process is repeated either sequentially or simultaneously to form multiple scan lines to cover a region of interest. The front end controller is responsible for controlling the timing and sequence of transmit and receive beams. Sampling rates used for analog to digital conversion in the front end can vary from 16 MHz to 50 MHz depending on system requirements. Most ultrasound imaging systems are capable of three major modes of operation: B mode, color flow, and Doppler mode. B mode operation results in a grayscale image that is used for examining tissue structures and organs. Color flow operation results in a color coded display of spatial distribution of mean velocity of blood flow superimposed on grayscale image. Doppler processing produces scrolling display of blood flow velocity distribution at a user specified location. Some systems are capable of displaying all three modes simultaneously. Common to all three is the initial stage where beam formed RF data gets down converted to baseband, filtered, and in most cases decimated. What follows this depends on the type of mode. Just like most embedded systems, ultrasound imaging systems need a system controller to carry out functions such as configure and control the signal path, events, and take appropriate actions, acoustic pressure and intensity levels, and ensure safety of patients. In this slide, you can see different parts of ultrasound machine, like you can see transducer, pulse control, central processing unit, CPU, disk storage, keyboard, display, and the printer. Now we are going to see procedure of ultrasound. Place a probe on a skin over the part of the body to be examined. Lubricating jelly is put on skin for better contact with the body. Probe is connected to the wire to the ultrasound machine, which is linked to the monitor. Pulses are sent from the probe through the skin into body. Ultrasound waves are back as echoes from various structures in the body. Echoes are detected by probe and sent to ultrasound machine through wire. They are displayed as a picture on a monitor. Operator moves probe around over surface of the skin to obtain views of different angles. It can be used to measure the different size. Advantages of ultrasounds are: in ultrasound, no needles or injections are needed and they are usually painless. They are less expensive. No ionizing radiation is used in ultrasound imaging. It gives a clear picture of soft tissues. It has been used to evaluate pregnancy for nearly 40 years. Doctors are provided with lots of useful information from the ultrasound. Ultrasounds can be applied in gynecology, anesthesiology, cardiology, gastroenterology, obstetrics, and urology. Figure 4 illustrates ultrasound image of a right kidney. Ultrasound images of right kidney can help doctors to evaluate the location of the kidneys, the size of the kidneys, the shape of the kidneys, blood flow to the kidneys. It can also help them to detect signs of injury, kidney stones, and tumors. Figure 5 illustrates renal ultrasound showing a renal cyst. You can see it is represented by an arrow. Figure 6 illustrates pregnancy ultrasound to check the condition of a baby. With this, I complete my today's lecture on ultrasound imaging. If you need any further information or clarification, feel free to contact me through my mail navin.devangan@bitdurg.ac.in. In my next lecture, I will be available with another interesting topics of biomedical instrumentation and sensors. Till then, goodbye. Thank you all.